400,000. It's documented, it's time-stamped, it's geolocated. That number doesn't count the dead, it counts failures. 400,000 equipment and device failures in the Texas electrical infrastructure, accurately recorded during 1 week in February 2021. A winter storm produced this, and now this failure map is available to any adversary who wants to use it as a blueprint for attack. In February 2021, Winter Storm Uri brought Texas to within 4.5 minutes of a total power grid collapse. Not partial, total. 246 people died. 4.5 million homes lost power. The economic damage reached $295 billion. All of this without a single weapon, without an attacker, just cold. Now you need to understand what 400,000 failures actually means. It's not 400,000 homes in the dark. It's 400,000 failure points in the infrastructure. Frozen sensors, stuck valves, generators shut down for safety, offline compressor stations, overloaded transformers, control systems losing response. Every single one of these points has an address. It has a log of exactly when it stopped working. It has a technician who tried to fix it. These are 400,000 individual failures that combined into a single systemic collapse. And the question no one is asking out loud is, an enemy reading this failure report has exactly what they need to do the exact same thing. But on purpose. You're going to understand today why the Dallas blackout is not a warning about the weather. It is an operational manual, handed over for free, to anyone who wants to use it. In 2024, United States intelligence agencies confirmed that Chinese military operations are already pre-positioned inside American critical infrastructure networks, right at this very moment. The failure map already exists. The capability to execute it has already been confirmed. All that's missing is the order to activate. The first page of this manual is the architecture. Texas is different from the rest of the United States in a way that matters more than anything else in this story. While most American states are connected to two major power grids, the Eastern Interconnection and the Western Interconnection, Texas operates in isolation. The Texas power grid is managed almost entirely by ERCOT, which controls about 90% of the state's electrical load. And ERCOT is not connected to neighboring grids in a way that allows large-scale power transfers during an emergency. This wasn't an accident. It was a deliberate decision made decades ago, driven by two things: rate control and evading federal regulation. If Texas connected to interstate grids, it would be subject to regulation by FERC, the Federal Energy Regulatory Commission. By keeping the grid within state borders, Texas preserved regulatory autonomy. In normal circumstances, that means local rates and less federal bureaucracy. In crisis circumstances, it means you're on your own. When Winter Storm Uri hit, neighboring states had power to spare. Louisiana, Arkansas, Oklahoma, they were operating normally. But Texas couldn't import that power in sufficient volume to make a difference. The interconnection exists, but it is limited to a tiny fraction of the necessary capacity. In practical terms, when Texas needed electrical help from the outside, there wasn't a pipe big enough to let that help through. Think about what this means strategically. One of the main consequences of a high-altitude EMP attack is exactly this: isolation. The affected area loses the ability to receive power from the outside because the transmission infrastructure is destroyed. Texas already has this isolation built into its design. Not because an enemy engineered it that way, but because local regulators and lawmakers decided to do so. The result is the same. When the collapse starts, there is no rescue coming from the outside. If you can't import power during a crisis, what happens when internal generation collapses? The answer starts with natural gas. In February 2021, natural gas was responsible for approximately 46% of Texas's electrical generation in the winter. It's the primary source. And natural gas has a vulnerability that most people don't know about. The gas supply chain relies on electricity to function. Read that again. Gas needs electricity. Electricity needs gas. When both go down at the same time, neither can rescue the other. You need electricity to operate the compressors that move the gas through the pipelines. You need electricity to keep the sensors at the control stations online. You need electricity to trigger the valves that regulate the flow. When temperatures dropped to levels Texas wasn't prepared to handle, poorly insulated sensors froze. Valves got stuck. Wellheads froze over. Compressor stations shut down. And then happened what engineers call a cascade. A gas plant that loses supply pressure automatically shuts down for safety. When it shuts down, the load it was supplying has to be absorbed by other plants. These other plants are pushed beyond their operational capacities. Some of them trip their own protection systems and shut down as well. The now redistributed load pushes the remaining plants past their limits. More shutdowns, less generation, more load on fewer power plants. The cycle accelerates itself. ERCOT began implementing load shedding, the famous rolling blackouts, on February 11th. The idea was to methodically cut power to parts of the grid while sparing others. But the generation collapse happened faster than operators could manage. The rolling blackouts turned into uncontrolled outages. Entire regions lost power not because they were selected, but because the system simply couldn't keep them online anymore. In the early hours of February 15th, ERCOT had lost so much of its generation capacity that the system was operating with a 4.5-minute margin before total collapse. 4.5 minutes. That's not a near miss. That's a system already in freefall. If ERCOT had lost any more capacity at that moment, the state would have entered a total blackout. An event where there is no longer enough generation to keep any part of the grid running. And a total blackout is a completely different category of crisis. Because recovering from a partial blackout is hard. Recovering from a total blackout requires an operation called a black start. And it takes weeks, possibly months. That distinction is what separates a power outage from a civilizational collapse. A black start is the process of rebooting a grid that has been completely shut down from scratch. You can't just flip a switch on the massive generators. They need electrical power to start. So you need black start generators, which are small power plants specifically designed to run without external power. You turn on those generators. You use their power to start larger plants. You use those larger plants to fire up even more. You gradually rebuild the grid from the ground up, section by section. Under normal conditions, this process takes weeks. Under extreme winter conditions, with equipment damaged by freezing, exhausted crews and scarce supplies, it could take months. Texas was 4.5 minutes away from having to go through that. Now think about the systems that would have failed first in that collapse sequence. Industrial control sensors, SCADA in the generation plants, automated valves in the natural gas supply chain, substation controls. Keep that list in mind. We're going to come back to it. A power outage turns off the lights. An electromagnetic pulse, an EMP, destroys the switches. That distinction is the analytical foundation for everything that follows. Right at this exact moment, as you read these words, there are high-voltage transformers operating in substations across the United States that have no manufactured replacement parts, no strategic reserve, no emergency stockpile. If one of them is destroyed today, by a storm, a failure, or a cyber command, the replacement lead time is 18 to 24 months. That's not an exaggeration. That is the assessment of the U.S. government itself. A high-altitude EMP is generated by a nuclear detonation above the ionosphere, typically between 30 and 400 kilometers in altitude. The detonation produces three distinct pulse components. E1 is the fastest component. It occurs in nanoseconds and induces high-voltage currents in any electrical conductor. This destroys chips, integrated circuits, microcontrollers, anything with embedded electronics, cell phones, computers, industrial control systems, the electronics in modern vehicles. E2 is similar to a lightning strike in its effect, slower than E1, but it adds voltage to already damaged systems. E3 is the slowest and longest-lasting component, similar to the effect of a geomagnetic storm, and it's what causes transformers to explode. High-voltage transformers are the critical bottleneck of this entire analysis. They are the components that convert high-voltage power from transmission lines down to the levels that reach homes and businesses. They are custom-built. The largest of them weigh hundreds of tons. There are no spare parts in stock. The United States does not maintain a strategic reserve. Most are manufactured overseas, primarily in South Korea and Germany. In an EMP attack scenario that destroyed transformers on a massive scale, the waiting line for a replacement would be years long. And during those years, there is no grid. There is no centralized electrical generation. There is no normally functioning hospital system. There is no refrigerated food supply chain. There are no large-scale communications. The difference between a storm-induced power outage and an EMP is not duration, it's recoverability. Texas lost power for days to weeks because the infrastructure was intact, just offline. An EMP destroys the infrastructure. It's the difference between a car that ran out of gas and a car with a blown engine. And now comes the part that most analysts don't explicitly connect. A well-executed cyber attack can replicate the physical effect of an EMP without using a single nuclear weapon. In 2007, the United States Department of Energy conducted a classified test called Project Aurora, which was later partially declassified. The test demonstrated that an attacker with access to an electrical generator's control system can send commands that force the generator out of sync with the grid, create extreme mechanical stress on the equipment, and physically destroy the machine, with no explosion, no physical weapon, just software commands. The mechanism is brutal in its simplicity. Power generators operate in sync with the grid's frequency, 60 Hz in the United States. When a generator falls out of phase, the resulting mechanical forces are devastating. Aurora demonstrated that an attacker can sequentially open and close breakers to purposely create this desynchronization. The result was what the test's security camera captured: a 2.25 megawatt generator suffering progressive catastrophic failure, spewing smoke and metal, mechanically destroying itself in a matter of minutes. The problem: the Aurora vulnerability is not fully patched across the entire United States grid. VRC acknowledges this. NERC acknowledges this. Regulations require some utilities to fix it, but not all of them. There are generation facilities in the United States today that remain vulnerable to this class of attack. In December 2015, Ukraine was the target of the first confirmed cyber attack against a civilian power grid in history. The Black Energy malware compromised the SCADA systems of 3 energy distribution companies. The attackers spent months inside the networks before executing. When they did, they remotely tripped the breakers at 30 substations, cut power to 230,000 customers, and overwrote the firmware of the control devices to prevent remote recovery, forcing technicians to physically travel to each substation to restore it manually. A year later, in December 2016, came Indestroyer, also known as Crash Override. Unlike Black Energy, which was adapted from existing malware, Indestroyer was designed from the ground up to attack electrical infrastructure. It was the first malware specifically built to interact with the industrial protocols that control power substations. It simulated the legitimate commands operators use to control the grid, making it invisible to normal detection systems. The target was Kiev. It managed to cut power for about an hour before being detected and stopped. What these attacks proved isn't just that it's possible to take down a grid with software. They proved that sophisticated attackers can stay hidden inside critical networks for months without detection, execute at a time of their choosing, and cause actual physical damage to equipment through digital commands. The cost to develop and deploy Indestroyer was estimated at a few $1 million. The Dallas Blackout cost between $195 and $295 billion. This asymmetry is no coincidence. It's the business model of cyber attacks on critical infrastructure. You spend $2 to $5 million to inflict $200 billion in damage. The math is not on the defender's side. And now we return to Dallas. Winter storm Uri followed a specific sequence of collapse. Temperatures beyond design parameters, control sensors failing, compressor stations stopping, gas flow dropping, plants shutting down, load redistributed onto the remaining ones, more shutdowns, loss of control over the load generation balance, and the system coming within 4.5 minutes of total collapse. The storm relented, the cold passed, the gas recovered, the plants progressively came back online. The grid stabilized within days. Now map the equivalent cyber attack onto that failure map. The difference isn't in the collapse, it's in the recovery. An attacker reading ERCOT's post-Uri reports, and these reports are public, would know exactly which systems failed first. They would know that the natural gas supply chain was the trigger point. They would know that sensors and control valves were the first to go down. They would know that the interdependence between electrical generation and gas supply created a feedback loop that accelerated the collapse. They would know that ERCOT lacks the capacity to import power on a scale sufficient to offset a catastrophic loss of internal generation. A sophisticated attacker wouldn't need to mimic the storm. They would need to do something simpler and more devastating: prevent the recovery that the storm failed to prevent. What a cyber attack adds that the storm didn't have is the ability to prevent that recovery. If the SCADA systems of the gas plants are compromised, operators cannot see the actual state of the equipment. If substation controls are under hostile command, the operator cannot remotely reconnect circuits. If the black start generators, the few plants specifically designed to boot up the grid from scratch, are specifically targeted by the attack, the recovery window expands from days to weeks. Uri showed what nature can do without even trying. An attacker with access to the right control systems could do the exact same thing, and then lock the door when recovery begins. What this means in human terms: in the scenario of a weeks-long blackout in the dead of winter, the first systems to fail after electricity are the water supplies. Treatment pumps need power. Then heating. Then communications, when the backup generators at cell towers run out of fuel, typically in 24 to 72 hours. Then the refrigerated food supply chain. Then hospitals, as their emergency generators are depleted. The order is documented. Uri demonstrated the early stages. An attack designed to extend the blackout would demonstrate the rest. This scenario isn't hypothetical. It's the scenario that adversaries have already positioned themselves to execute. In February 2024, American intelligence agencies, CISA, NSA, FBI, and international partners issued a joint warning confirming what had been suspected until then. The Chinese threat group Volt Typhoon had infiltrated critical infrastructure networks in the United States. Not theoretically, not in the past. At that very moment. The warning didn't say China might have tried to get in. It said that China was already inside. Volt Typhoon isn't a group of opportunistic hackers. It's a military intelligence operation. They didn't steal data. They didn't execute visible attacks. They got in, stayed quiet, waited. The technical term is land and wait. The goal isn't espionage, it's pre-positioning. The timing is calculated to coincide with the exact moment the United States would need maximum mobilization. A crisis in the Taiwan Strait, for example, or a direct conflict in the Pacific. It's not about stealing secrets. It's about turning off the lights when you need them most. Over in Russia, the Sandworm Group, linked to the GRU military intelligence, is responsible for the attacks on Ukraine in 2015 and 2016. The exact same group is documented as operating against Western infrastructure. They're not a new player. They have an operational track record, field-tested tools, and proven political motivation. Now combine that with what the American regulatory side hasn't fixed. The NERC CIP, Critical Infrastructure Protection. Standards define the minimum cybersecurity requirements for electric utilities. The problem is structural. NERC CIP was built to handle known threats, using a compliance logic based on periodic audits. It wasn't designed to detect long-term zero-day intrusions that leave no known signature. A sophisticated attacker using legitimate tools, like Volt Typhoon does, slips right past compliance checks because, technically, they aren't breaking any detectable rules. And the patch for the Aurora vulnerability still doesn't cover all utility companies. That's FIRS's own assessment. In a large-scale Aurora attack scenario, where multiple generators are physically destroyed via cyber commands, the replacement queue for transformers would create a recovery bottleneck measured in years, not months. The regulatory math is simple and grim. The attacker only needs to succeed once. The defender needs to succeed every single time. This asymmetry isn't just rhetoric. It's the operational principle that defines why pre-positioning works as a strategy. You don't need to win right now. You just need to be ready to win when it matters. In February 2021, a storm brought Texas within 4.5 minutes of total collapse. Not a weapon, not an attack. A winter storm that the state was unprepared to face for documented, known, and fixable reasons. What has changed since then? ERCOT's isolation structure remains intact. Texas is still not connected to the eastern and western interconnections in a way that allows for large-scale emergency power imports. There have been winterization efforts at power generation plants, but the implementation was partial, criticized by independent auditors, and investments fell short of what was needed. The interdependence between natural gas and electrical generation, the feedback loop that nearly brought down the system in 2021, continues to be the central structural vulnerability. The post-Uri reports are public. The failure maps are public. The cascading sequences are documented and easily accessible. An intelligence engineer in Beijing or Moscow who wanted to understand how Texas collapses has the exact same document that ERCOT engineers used to try and fix the system. The difference is that ERCOT used those documents to make incremental improvements. An adversary would use them to build an attack plan. Dallas 2021 isn't a warning about climate preparedness. It's an operational blueprint. Nature conducted an uncontrolled test of systemic collapse, documented the results in precise technical detail, and published the findings. No adversary had to spend a single dime to figure out how the Texas grid fails. The storm did all the research for them. And what makes this strategically different from any other infrastructure vulnerability is the time factor. A high-altitude EMP is irreversible. You destroy it, and the damage is done. A storm-induced blackout can be recovered from because the infrastructure remains intact. But a Cyber-EMP executed with access to SCADA systems, specifically targeting the failure points documented by Uri, with components designed to block recovery. That combines the worst of both worlds. It causes physical damage via digital command, blocks recovery via system control, and exploits the structural isolation that Texas has chosen to maintain for regulatory reasons. Volt Typhoon is already inside critical American networks. Sandworm has field-tested tools. The Aurora vulnerability isn't fully patched. Transformers lack a strategic reserve. And ERCOT still operates in isolation, with no large-scale external relief capacity, sitting on a power grid whose failure map was generously provided by a winter storm. The question the title of this video asks is, what does the Dallas blackout prove about a Cyber-EMP attack? The answer is that it proves it works, not theoretically. On record, the collapse sequence exists. The structural vulnerability exists. The adversarial capability exists. The pre-positioning exists. The only thing that hasn't happened yet is the political decision to pull the trigger. The final asymmetry: 4.5 minutes separate Texas from a total blackout that would take weeks to recover from. The storm got to this point without even trying. A weapon designed for this wouldn't waste those 4 minutes. The Dallas blackout was an unintentional demonstration of an attack scenario that adversaries have the capability to execute intentionally, are already pre-positioned to execute, and have strategic reasons to keep as an option. This channel keeps covering what the documents and data actually say. Subscribe, because the difference between understanding this kind of threat and not understanding it might be exactly 4.5 minutes.